Welcome back to Advanced Function, MHF4U1, Rates of Change chapter. Lesson number 2, we are going to take a look at estimating instantaneous rate of change. We also want to take a look at ways of identifying the slope of a tangent line. So instantaneous rate of change, it means that you are finding the rate of change at that instant, meaning at one point. But as you can see, with the slope formula, you need 2 points, 2 defined points to find the steepness of a line. But unfortunately, you can't really find the steepness, the slope of a line, by using 1 point. What you have to do is pick 2 points. So for example, let's say I want to find the steepness of a line at this point, at A, at F and A. And then you're going to pick another point and define that the difference from A to the next point is differ by plus h. So as you can see, the closer the point to the given A, the more accurate the rate of change is going to be. So we always say for the instantaneous rate of change, we will be using a difference quotient, which is instantaneous rate of change is equal to f at a plus h minus f at a. And we have to define by saying let h be plus or minus 0.01. So we want the minimal, the difference, to be 0.01, minimal as possible. Okay, so how did I arrive at this formula? Well, actually, it is a secant formula, but as you can see, if x1 and x2 are approaching a number xa, then the average rate of change, it will turn into an instantaneous rate of change at x equals a. Okay, so therefore, it is actually a secant line, which is the rate of change is f at a plus h minus f at a over a plus h minus a. But as you can see, a and a cancels out. So that's why you're left with h. So in this case, assuming that the h is very, very minimal, we're actually then looking for the rate of change at that instant point. So the instantaneous rate of change is the same as we call the slope of the tangent line. So previous chapter, we said a secant line. A secant line is where there are 2 points on a curve or a line. But on the other hand, the tangent line is 1 point on the line. So there are 2 ways that we could find the instantaneous rate of change. So first way, we did mention that we have to let h, the difference, to be very minimal. Another way to look at it is by using a limit. But unfortunately, limit is another big concept. So what we could say over the equal sign, we're going to say as h approaches 0. And then f at a plus h minus f at a over h. So that's another instantaneous rate of change that I would definitely highlight by saying that h with the arrow means approaching 0. So we want the h to be minimal as much as possible. Okay, so this way will be the most accurate way to finding the rate of change at that point. So I will show you both ways how we can incorporate this. So again, a reminder, a tangent line is where only touches one point on a curve. So as you can see, we're given point Q, and as Q approaches the point P, the secant line from here, and then as it approaches, it actually becomes a tangent line that touches only one point at point P. Okay. So question 1. From a 10-meter platform tower, a diver performs a handstand dive. So his height, which is in meter, above the water at t seconds is modeled by this polynomial expression. So use the difference quotient to estimate the rate of change of height when t is 1 second. So it is asking us to find the rate of change, but it's specifically an instantaneous rate of change. How do I know? Because they give us a defined 1 point. They're asking find the rate of change at that instant 1 second. So let's write down the instantaneous rate of change. Formula is equal to F A plus H minus F at A over H. So we're going to do method number 1, meaning we're going to say let H, the difference, be 0.01. So I'm going to let it as positive. So what does that mean? We know what A is. A is 1 second. So therefore, F at A plus 0.01, it's going to be 1.01 minus F at 1 is over 0.01. So what I'm going to do on this side is so in this case, we're using the distance, so D at 1.01. I'm going to plug in 10 minus 4.9, 1.01 squared. So once you evaluate it, you get 5.00151, and then distance at 1 second, so 10 minus 4.9, 1 squared, and that will give me 5.1. So therefore, 5.00151 minus 5.1 over 0.01. So once you evaluate it, you will get negative 9.849, and the unit will be distance, which is meter per second. So therefore, by using the method number 1, by letting the H, the difference, to be 0.01 at 1 second, he is falling. He is falling at 9.8 meter per second. So I decided to omit the negative by replacing with falling. Falling represents that it's going down, the negative sign. Okay. Now let's see. So what if we were to use the method number 2, approaching? So method number 2, again, it's the same formula, instantaneous rate of change, F at A plus H minus F at A, H. So this time we are going to say above the equal sign, we're going to say as H approaches 0. Not 0.01, but like literally approaching 0. So what we're going to do is we are going to, so when you're writing approaching, you have to write it for each line of the equal sign. So we're plugging A, we know it's 1 second, plus H, minus F at 1 over h. So in this case, we are going to plug in it's 1 plus h into my input. So 10 minus 4.9, 1 plus h squared. So this is algebra again. So 10 minus 4.9. So we're going to expand this. It's going to be 1 by doing a FOIL. It's going to be 1 plus 2h plus h squared. And then you're going to do the distributive property. 10 minus 4.9 minus 9.8 h minus 4.9 h squared. So let's combine the like terms of 10 and negative 1.9. So negative 4.9 h squared minus 9.8 h plus 5.1. So we have evaluated. Now, what if we were to plug in 1 into the function? It's 5.1, what we just got before. So therefore, as h approaches 0, so we know that it's going to be negative 4.9. So I'm replacing this with what we got on the side, negative 4.9 squared minus 9.8 h plus 5.1 minus, we know that the function when input is 1 second, it's going to be minus 5.1, which is this one, over h. So you will notice that this and this cancels out. And you will also notice that h and h cancels out in the denominator and the numerator. So it cancels, and cancels. So you get negative 4.9. Don't forget, h approaches 0. H minus 9.8. Now that we cancel the denominator, we can actually plug in 0 into h. Before, we weren't able to because it would be undefined in the denominator. So once I plug in h as 0, you no longer write h approaching 0 above the equal sign. So we are going to plug it in, minus 9.8. So then it becomes 0. So therefore, my answer is going to be negative 9.8. So we can see that as we get exactly the same answer as before. This will be the most accurate because you are not defining h to be greater than 0. So therefore, at 1 second, he is falling. Falling at 9.8 meter per second. Okay, and that is your final answer. So whichever you prefer, it could be approaching 0 or h equals 0.01. It's up to you. But if it's polynomial function, like in this example, I would definitely recommend as h approaching 0, as it gives you the most accurate answer. So here's another type of question, number 2. So we're given a function on the right. Part A, draw the tangent line at each point on the graph. Okay. So the first point, this is a unique one. We are going to get to this later, but if you have anything that is V-shaped, the tangent line is actually undefined here. Okay, so there is no tangent line here. So M, the slope of the tangent line does not exist here. Okay, so anything with the V shape, it does not exist. The tangent line over here will look like this. The tangent line here, it looks like it's horizontal. The tangent line here, oh, it's a vertical line. And the tangent line here, it looks something like this. So all the tangent lines should be a straight line. Now part B. For each point, find the slope of the tangent line that is negative, 0, positive, or positive, negative, infinity, or does not exist. Okay, so we did this already. For the first part, we said that the slope, when it's V-shaped, it does not exist. As you can see, as I'm reading from left to right, the slope is increasing. So the slope here is going to be positive. In this case, if you have a horizontal slope, that means the slope is going to be 0. That is the slope of the tangent line. Now here, it's a vertical line. So every time you have a vertical line, and the graph is decreasing. So in this case, we say the slope is negative infinity with any vertical line. Okay, so it could be positive or negative, but as we can see, because the graph is going down, we say it's decreasing by negative infinity. And then over here, it's going down. So in this case, the slope is going to be less than 0. Okay, now there are 3 types of intervals where you could use with define h, a 0.01. So for example, let's say we have a curve, okay? So we are looking for the instantaneous rate of change at A. Now there are 3 possibilities that you can choose. The first one is called a preceding interval. A small interval below the chosen point. So the preceding interval in this case, I will be choosing below A. Okay, so it will be anything that is smaller than A with A. So it could be like A minus H. The central interval is a small interval surrounding this chosen point. So we will assume, so this is my chosen point. So I will be choosing, right, 2 points that's making my the chosen point right in the middle. So it will be A plus H. So I'll be using A plus H and A minus H to find the slope. And lastly, the following interval is a small interval above the chosen point. So it's above. So in this case, I'll be using A and A plus H. That is beyond my chosen point. So given the 2 points, you'll be able to find the slope, but we have to make sure that the H stays at 0.01 or less to make it minimal difference. So this is a careful look at the formula. For preceding interval, instantaneous rate of change is defined by this. As we saw, the chosen point A and right before the chosen point. Okay. Again, H, we want it to be a very small number. The smaller the H, the more accurate your instantaneous rate of change is going to be. The central interval is the combination of preceding and following. So A minus H and A plus H. And this is the formula for instantaneous rate of change. And lastly, the following, which is the greater than the chosen point, which is A plus H minus F at A. So let's do some practice question. So we are given a function f at x, and it wants us to find the instantaneous rate of change at x equals 1 by using the difference h to be 0.01. Okay, so preceding. So preceding means that we are going to choose my first point to be x1 will be 1, and the preceding, which is before, it will be x2. So it will be this will be x2, and then the before x1 will be 1 minus 0.01, which is 0.99. Okay, so let's see. So instantaneous rate of change is equal to f at 1 minus f at 0.99 over 1 minus 0.99. Okay, so we are going to plug in 1 into my function over here. So plug in 1 by 2, 1 cubic plus 1. And once you evaluate it, you're going to get 3. So it's going to be, let's write it in vertically. So 3 minus 2 times 0.99 cubic plus 1 over 0.01. So once you evaluate it, it's going to be approximately 5.9402. That is my slope of the tangent line at 1 second, or 1. Okay, what about the following interval? So following interval means after my chosen point at 1. So x1 will be 1, and the following, the after point, is going to be 1 plus 0.01, which is 1.01. Again, instantaneous rate of change, f at 1.01 minus f at 1 over 1.01 minus 1. So same thing, it's going to be, I'm going to plug in 2 times 1.01 cubic plus 1 minus 3 over 0.01, which will give you approximately, once you evaluate it, is 6.0602. That is going to be my following interval at 1. So it's very close in number, okay? Okay, so lastly, what about the central interval? So central interval is right in between 1. So x1 will be 1 minus 0.01, which is 0.99. And x2 is going to be the after, so 1 plus 0.01, which is 1.01. So it's right in between. So instantaneous rate of change is equal to f at 1.01 minus f at 0.99 over 1.01 minus 0.99. Okay, so from the previous, it's exactly the same thing. So I'm going to 2 1.01 cubic plus 1 minus 2 0.99 cubic plus 1, and then it's going to be 0.02. So once you evaluate it, it's about 6.0002 instantaneous rate of change. Okay, now what can you conclude? So this number, if you take a look from the previous number, it's right in between. So this is the lower end, preceding, and this is the higher end, 6.06. And this is the best estimation. The reason is because it's right in the central range of the preceding and the following. So therefore, the exact value for the instantaneous rate of change is going to be 6. Okay, if we were to use as h approaching 0 method, then we will get exactly the rate of change at that instant.